Good day to all of you. Today we shall discuss on the topic pipelining. This comes in chapter 8 of textbook Computer Organization 5th edition by author Carl Hamacher. Our sincere acknowledgement and thanks to Carl Hamacher. Figure shows processor and main memory. So processor accesses the data and instructions from main memory directly. We store for permanent storage our program and data in secondary memory. For execution, it should be brought and be kept in main memory. So processor accesses one by one instruction and data from main memory and executes this. It takes considerable time. To avoid this, a copy of program and data is maintained in cache memory. Cache memory is the faster memory that comes between processor and main memory. So hence it can provide the needed instructions and data that is copied from main memory very fast to the processor. Hence access time is reduced and speed of the computer increases. So the speed of execution of programs is influenced by many factors. One way is underlying circuit in any computing device. If it is made up of advanced technology, then that device can work faster. Another possibility is whatever hardware is involved, so many operations are performed simultaneously, means at the same time. Hence, the total time taken for the execution will be reduced. So, pipelining comes in the second category of improving the performance of a computer. Figure shows sequential execution of three instructions I1, I2, I3. F1, E1 are the fetch and execute phases involved in the execution of instruction 1. Accordingly, all the three instructions have two phases, fetch and execute. So they are executed one after the other. So if one clock cycle is needed to execute one phase, totally 6 clock cycles of time is needed to complete the execution of all the three instructions. This is the case of sequential execution. Next, we shall consider the hardware where there are two independent units, instruction fetch and execution units. In between, we have for temporary storage interstage buffer B1. So, first instruction is fetched. It is stored in B1. From there, it is given to execution unit, and execution unit will be executing first instruction. During that, instruction fetch unit will be free. It will have brought the second instruction and be deposited in interstage buffer. So the buffer is needed to enable execution unit to execute the instruction while the fetch unit is fetching the next instruction. The results of execution are stored in the destination location specified by the instruction. So in this way, number of operations performed per second will be increased, though the elapsed time for execution of each operation is not changed. Because of simultaneous operation of many activities, the total time needed to complete a whole activity is reduced. So pipelining is an effective way of organizing concurrent activity in a computer system. So this is what is pipelining. What is pipelining? Pipelining is an effective way of organizing concurrent activity in a computer system. That is, in a computer system performing several activities at the same time or simultaneously. Figure 8.1 shows basic idea of instruction pipelining. Here in the figure we can see three instructions I1, I2, I3. For each instruction execution there are two phases, fetch phase and execution phase. F1, E1 are the fetch and execution phase of instruction 1. F2, E2 are the fetch and execute phases of instruction 2. F3 and E3 are the fetch and execute phases of instruction 3. So during first clock cycle, instruction 1 is fetched from main memory and it is copied into processor register. During second clock cycle, that first one instruction which is fetched and given to processor register, that will be executed simultaneously. At the same time, fetching of second instruction is done. During third clock cycle, execution of second instruction is done. At the same time, fetching of third instruction is performed. During fourth clock cycle, execution of third instruction is done. Like this, in 1, 2, 3, 4 clock cycles, the execution of all three instructions is over. This is what is pipeline execution, that is performing several activities simultaneously at the same time. Here, that is the basic idea of instruction pipelining. The processing of an instruction may not be divided only into two steps, that is fetch and execute. For example, a pipeline processor may process each instruction in 4 steps. The 4 steps being as follows: F for fetch, D for decode, E for execute, and W for write. In fetch phase, the instruction is read from main memory and copied into processor register. In decode phase, whatever instruction is loaded in processor register, that is decoded, means it is resolved what operation to do and where are the operands, and that information is conveyed to processor. In execute phase, the processor actually does the operation specified in the instruction and on the operands that are told in the instructions. In write phase, whatever result is obtained by the processor, that is stored in destination location. Figure 8.2 given here shows a 4-stage pipeline. So 4 instructions are shown here: 1, 2, 3, 4. For each instruction execution, there are 4 stages: 1, 2, 3, 4, or 4 steps. The first phase or first step is fetch, next decode, execute, and write. F1, D1, E1, and W1 are the 4 steps involved in execution of instruction 1. So in the first clock cycle, the instruction 1 is fetched. In second clock cycle, instruction 1 is decoded. At the same time, instruction second is fetched. In third clock cycle, the first instruction is executed, second instruction is decoded, and third instruction is fetched. In fourth clock cycle, the whatever result is produced after execution of first instruction, that is written onto destination location. So first instruction execution is over here. So during write phase of first instruction, execution of second instruction is done. At the same time, decoding of third instruction and fetching of fourth instruction is also performed. During fifth clock cycle, the write phase of second instruction is done. That is, whatever result is obtained after the execution of instruction 2, that is written on to destination location. At the same time, execution of the third instruction and decoding of fourth instructions are performed. During sixth clock cycle, write phase of instruction 3 is present. That is, after execution of instruction 3, whatever result is obtained, that is written on to destination location. At the same time, execution of fourth instruction is done. During seventh clock cycle, that is the last clock cycle, during which write phase of fourth instruction is performed. That is, after the execution of instruction 4, whatever result is obtained, that is written on to destination location. So that completes a 4-stage pipeline, means in pipeline manner the execution of 4 instructions is over. So totally 7 clock cycles it takes. If sequentially done, it would take 4 stages. After that, another 4 stages. So like this, 4 stages sequentially, each for instruction 1, 2, 3, 4, and hence 4 4s are 16 clock cycles would be needed. With pipelined kind of execution, it is reduced to 7 clock cycles only. This shows that pipelining enhances the speed of execution. That is, overall speed of the execution is increased, though the time taken for each operation is not changed. This is the hardware organization that is required for 4-stage pipeline. It has fetch unit, decode unit, execution unit, and write unit. These can work independently. In between we have temporary storage area, that is buffer B1, B2, B3. So during first clock cycle, first instruction is fetched and it is kept in buffer B1. So during second clock cycle, decode unit will take the first instruction from buffer B1. At the same time, the fetch instruction will fetch the second instruction. During third clock cycle, whatever decoded instruction which is stored in B2, that is given for execution. Then second instruction, whatever was fetched and kept in buffer B1, is given for decoding to decoding unit, and the third instruction is fetched and kept in buffer B1. During fourth clock cycle, whatever first instruction was executed, now it was kept in buffer B3, it is given to write unit. So this will store the result into destination location. This is how after 4 clock cycles of time we have one instruction execution completed. Okay, so such kind of independently operating 4 units are used along with in between interstage buffers in performing 4-stage pipeline. Okay, so next we shall discuss what is the role of cache memory. So in pipelining, each stage in pipeline is expected to complete its operation in one clock cycle. Hence clock period should be sufficiently long to complete or to wait till the task being performed in any stage. If different units require different amounts of time, the clock period must allow the longest task to be completed. A unit that completes its task early is idle for the remainder of the clock period. Means if clock period is small, it may not be enough to complete the task in a stage, or if it is long, a fast acting unit may go idle. Hence pipelining is most effective in improving performance if tasks are performed in different stages require about the same amount of time. This consideration is particularly important for the instruction fetch step. The clock cycle has to be equal to or greater than the time needed to complete fetch operation. However, the access time of main memory may be as much as 10 times greater than the time needed to perform basic pipeline stage operations inside the processor, such as adding two numbers. So that is, fetching instruction from main memory is little bit slower, 10 times slower when compared to the basic pipeline stage operation inside the processor, that is addition of two numbers. Thus, if each instruction fetch required access to main memory, pipelining would be of little value. So that is, whatever program and data we have kept in main memory, for each instruction if we make the processor to access it from main memory only, it takes more time and it is not possible to design pipeline stage of equal time or equal length. So the use of cache memory solves the memory access problem, that is accessing the data and instruction from main memory by the processor is delayed one. It is a problem in designing equal time pipeline stages. In such case, cache helps. In particular, when a cache is included on chip with the processor, access time to the cache is usually the same as the time needed to perform other basic operations inside the processor. This makes it possible to divide instruction fetching and processing into steps that are more or less equal in duration. Each of these steps is performed by different pipeline stage and the clock period is chosen to correspond to the longest one. So because of cache, accessing of program and data from main memory which would be delayed is eliminated, because a copy of that which is maintained in cache memory, from cache memory only directly it is given to the processor. Hence access time is reduced and each of the steps performed by different pipeline stage now will have almost same duration. That is the role of cache. Next, we shall discuss on pipeline performance. In any pipeline, depending on how many stages are there, that total time or that many number of clock cycles will be consumed for the completion of one instruction execution. Right? In four-stage pipeline, because four stages are involved for completion of one instruction, then 4 clock cycles of time will be consumed. If 2 phases, then 2 clock cycles of time will be consumed for execution of one instruction. This way, the total time taken for one instruction execution depends on the number of stages involved in pipeline. And the second point is, it is assumed that in pipeline performance, each stage in the pipeline consumes 1 clock cycle of time. Unfortunately, this is not the case. Here, if you consider this figure, it shows 4-stage pipeline, the ideal case one. That is, all the phases consume only 1 clock cycle of time. And this figure indicates the practical or non-ideal kind of 4-stage pipeline. Here, decode phase of instruction 3 is delayed by 2 clock cycles. Here, in 1 clock cycle, it would have been over. Second and third, totally 3 clock cycles it is consuming, during which fetching of 4th instruction is also done. Hence, decoding of 4th instruction must wait for extra 2 clock cycles. Observing delay in completion of any stage or number of clock cycles consumed more is called as pipeline stalling. So, any condition that makes the pipeline to wait or stall is called as hazard. We have 3 types of hazards: data hazard, instruction hazard, structural hazard. Hazard means delay in the pipeline completion or pipeline taking more than 1 clock cycle. If the processor requested data is not available, means if it takes more time from memory to be accessed, then delay in that fetch phase will occur. That is called as data hazard. Then while accessing instruction from cache memory, if it is not available in the cache, which is called as cache miss, then some delay will be there in accessing the instruction for cache, and due to which the pipeline stage will stall. That is called as instruction hazard. The structural hazard means during write phase, when result is going to be written onto memory, if that single memory is shared by 2 events, then that will be delayed. And if data and instruction are referred from same memory, then also the structural hazard does take place. So here what in figure we can see: delay in decoding, delay in fetching. A data hazard is any condition in which either the source or destination operands of an instruction are not available at the time expected in the pipeline. Hence, that fetch phase in the pipeline stalls, waits, or its completion gets delayed. So there are a variety of reasons. One of the pipeline stages may not be able to complete its processing task for a given instruction in the time allotted. For that, there are variety of reasons. So here we can see 4 independent units: fetch, decode, execute and write, which are used in the 4-stage pipeline. So the stage 2 and in turn stage 1 are blocked from accepting new instructions because the instruction in B1 cannot be overwritten. That is, the point is, if decoding is delayed, the next instruction cannot be fetched and kept in buffer memory. So it has to be delayed. That activity should be delayed till decoding is over. So the pipeline may also be stalled because of delay in the availability of instruction So that was data hazard, and this is non-availability of instruction in time, that is called as instruction hazard as stated already. So here the fetch phase is being delayed. Instruction execution steps in successive clock cycles. Pipeline stall caused by a cache miss in F2. Means an instruction was being fetched from the cache memory. Because it is not copied from the main memory into the cache, at that time it is not available, due to which non-availability of the instruction happens and fetch phase in the pipeline stalls, prolongs, or it has to wait till it is fetched. So the instruction fetch unit must now suspend any further fetch request and wait for instruction to arrive. The third type hazard, which already stated, that is structural hazard. This is the situation when two instructions require the use of given hardware resource at the same time. The most common case is in which this hazard may arise is in accessing the memory. Many processors use, that is why, separate instruction and data caches to avoid this delay. In general, structural hazards are avoided by provided sufficient hardware resources on the processor IC. So, pipelining is a technique used to build fast processors. It improves computer performance. It also needs sophisticated compilation techniques. For that purpose, optimized compilers have been developed. And these compilers may rearrange the sequence of operations to use pipelining advantageously. And this is okay as long as this rearrangement of instruction doesn't change the functionality of the program. It is very important to understand that pipelining doesn't result in individual instructions being executed faster. Still, each instruction take the same original time, but due to overlapped execution or simultaneous execution of different stages in the pipeline, the overall execution time of the program is reduced. So it is the throughput that increases, means per second totally how many instructions are executed, that actually increases. Anytime one of the stages in the pipeline cannot complete its operation in one clock cycle, then the pipeline stalls, waits, or prolongs in time, or it cannot get completed in one clock cycle of time, and some degradation in performance occurs. An important goal in designing processors is to identify all hazards, data hazards, control hazards means instruction hazards that may cause the pipeline to stall, and we have to find ways to minimize their impact. That completes the discussion. So, what was the topic? Pipelining. In that we discussed the basic concepts, that is main memory, cache memory, and processor, how over the system bus program and data are copied from main memory to cache, and from there at faster rate made be available to processor, that is there in basic concepts. Then we studied what is the idea of pipelining, that is overlapped fetch and execute cycles in case if execution of an instruction has two phases. Next, with the idea of pipeline, we moved on to four-stage pipeline. Then what hardware is required to implement four-stage pipeline? Next, what is the role of cache memory in pipelining? And we ended the topic with the pipeline performance. That was the discussion on pipelining. I hope you understood. Thank you.